So let's say we have a quadratic function that is graphed here. So we got a parabolic curve, and we want to match the equations for each of these graphs here. So what I'm going to do is we're going to identify all the key points of each parabola or quadratic curve here. And then with those points, then we can start matching them with the equations. So I'm going to look at the x-intercepts here of each. So let's say for graph A, and then we have a vertex over here. So I'll write V for vertex. Now for graph B, we're going to do the same thing. So for the roots, and I'll just write roots instead of x-intercept here. So for the roots, they're going to be at x equals, there's one here and one here. And then the vertex right over here. And then for graph C, we're going to do the same thing. So for the roots, right, it goes here. And then the vertex right over here is at about -1 and 8. We're going to write for each graph is the y-intercept, and so that's where it crosses the y-axis. So if I go to graph A, the y-intercept appears to be at 0, so we're going to write y-intercept at 0. Then for graph B, the y-intercept appears to be at -2, so we're going to go y-intercept at -2. And then for C, it looks like it's at 6. So we're going to write y-intercept is at 6. There are 3 forms of the quadratic function, or the quadratic equation here, but of the ones listed on the side that we're going to choose from here, there's only 2 forms that I see present, which are the standard form and the factored form. Now, when it comes to the standard form, the C represents the y-intercept. And then the A tells us if it opens up or opens down. And if it opens down, then it's going to be negative, and if it opens up, it is going to be positive. And this is important because we could see that for graph C here, this one opens down. So then we know that your A is going to be a negative value, whereas for the rest of these, we're looking for positive A values here. So now, based on these properties, when we look at, let's say, starting with graph C, if it has the y-intercept of 6, then it means that the C value in the standard form should be a 6, which we could see applies to the equation 4 over here. So in this case, then since C opens downwards, the A should also be negative, which we also see here. So it is very likely that this equation belongs to graph C, since it has the negative in front, indicating that it opens down, and it crosses the y-axis at 6. Now, as for the other ones, if we look at equation 5, it has no C value here, which means that C is 0. And so if we're looking for a graph in which the y-intercept is 0, well, that is graph A over here, and it's positive. The A should be positive because it opens upwards. So graph 5, or I should say equation 5 here, would be well suited for graph A. And then when we look at graph B, which has a y-intercept of -2, and then we're looking for a function that has the C value of -2, which we could see here, and it should also have a positive A value since it also opens up here. And so equation 6 matches graph B, so I'm going to put that here. Now finally, to assign the proper equation in factored form to each graph, we're going to look at the roots. The s and the t here are the roots of a quadratic equation. And so since we see that the roots are -2 and 0, we're going to look for which of the equations in factored form has a -2, which it would be, remember that you would reverse the sign inside the brackets since these brackets are set to 0. So we could see that there's that -2, I should say, would be x plus 2. So if I were to rewrite that here, that'd be x plus 2, which I could see that equation 3 works here. And when you have an x that is written not within brackets, that means that the x is 0, because you wouldn't write x plus 0. You would just write x, because it's redundant to write 0 inside a bracket. So this equation makes sense since 3x would indicate that x is 0. So now in terms of that 3 though, again, we don't know what the exact value of the A equation would be. But given that it's a positive value, indicating that it should open up, that would also match this graph here. So for our second equation in factored form, we're going to assign it 3x and then x plus 2. What I do want to also draw your attention to with regards to the A values, that we could see that A should be the same in both the factored form and the standard form. So 3 here, which means it should be 3 there as well. And so this is the equation that matches that function here. Now for graph B, we see that the roots are -1 and 2, which means that it would be x plus 1 and then x minus 2 within brackets. And so when we look at that graph here, or I should say the function, if we look at number 1, we can see that it's written as x plus 1 and x minus 2, and that the A value is 1 over here, and the A value was 1 in the standard form. So because of the x values here, this too seems like a match for this function here. So x plus 1 and x plus 3, again, indicating that it has roots of -1. And sorry, not 3, it should be 2. I made a mistake here. That should be -2. And then finally, for the graph C here, with roots at -3 and 1, well, that would be x plus 3, and this would be x minus 1. And we could see that this matches this over here. And the A value would be -2 from the standard form, which we see also matches the factored form here. And so that would be the appropriate function here as well, based on everything that we're seeing in the graph. The greater solution to the quadratic equation 9x squared plus 4x minus 1 equals 0 rounded to the nearest hundredth is. So when they say the greater solution, we're acknowledging the fact that there are two x values. And so between the two of them, which one is greater? So there are two ways that you could solve this. What you could try and do is you can try and factor this first. However, none of these factors actually add up to the middle term. So this is non-factorable. Now, when it's non-factorable, then what we can do is use the quadratic equation to get the zeros or the x values, or you could say the solutions to this equation. Now that plus or minus over here means that there's two calculations, and so by doing negative b plus b squared minus 4ac over 2a and then negative b minus that same equation, we get 2x values. And so when we calculate this here, our first x value when we use the minus sign ends up being about negative 0.62284. And then the second value when we use the plus sign is about 0.17839. And so this is the bigger value, and when it's to the nearest hundredth, then that'd be 0.18. So for this question, we're asked to use the discriminant in order to determine the nature of the roots for each quadratic question. So you can algebraically solve for roots, but it doesn't mean that they're actually there. So in this case, what we're going to do is when we say use the discriminant, we're talking about this formula here. So we give it's d is equal to, and it's b squared minus 4ac. And as previously mentioned, there are values that kind of tell us how many real roots our quadratic function has. If we apply this formula here to every single one of these, let's see what values we get. And if there are, let's say, 2 real roots, we're going to go ahead and solve for those roots using factoring of the quadratic formula. The graph of y equals ax squared plus q intersects the x-axis in 2 places when. So when we're talking about intersecting with the x-axis, what we're talking about is a quadratic that should have 2 real roots. Okay, and to kind of give you conceptually what that would mean is, imagine you have a graph of a quadratic. If it has 2 real roots, then your graph would show that it intersects with the x-axis twice here. Now, if we're thinking about the standard form of a quadratic, so f at x is equal to, this would be ax squared plus bx plus c. And this is important to note because the way that this is written here is it's kind of without a b value. Now, if it's missing that b value, then that means that for this formula over here, your b must equal 0. And so the way they would normally write it would be y is equal to ax squared plus, imagine it said 0x plus q. Well, there's no point in writing 0x because no matter what x is, it's going to be 0. So they're only writing just this section over here. That being said, when we want to figure out how many real roots a quadratic function has, we have to figure out or calculate something called the discriminant, which is the part in the quadratic formula that goes under the root. And this formula over here, which is the discriminant formula, has some guidelines based on whatever the calculated value is. So for this question, what we're going to do is we're going to test each and every one of these scenarios, A through D, by plugging in the B value, A, and C values into this discriminant formula here and see which one gives us 2 real roots based on these rules here. So for the first scenario presented in A here, A is greater than 0 and Q is greater than 0 as well. So we said that B was 0. We're going to say that A refers to this portion here, and Q would be the C part of our quadratic formula here in the standard form. So In this case, I'm going to say that A is 1 and Q or C has to be 1 as well, as long as it's greater than 0. And so if we plug that into the discriminant, that means that D is less than 0. So this here would have no real roots. Now for B, we have A is less than 0 and Q or C is less than 0. So let's give A value of -1 and then Q or C a value of -1. And then we're going to plug it into this discriminant formula over here. So that would still end up with us getting -4 for the discriminant value, which again would be no real root, so it can't be this one either. Now that only leaves us with one option left, but let's double check it anyway in case this could be a faulty question. So we're going to, again, apply these scenarios. So let's say A is greater than 0, which means that A would equal to 1, and Q is less than 0. So let's make it -1. We're going to plug these into the discriminant formula as follows and see what we get. And this would cause our discriminant to have a value of 4. And according to the rules here, if it's greater than 0, then it has 2 real roots. So this is the option that is correct. When y equals 2x squared minus 8x plus 2 is written in the form y equals ax minus p squared plus q, the values of p and q are. So this here, remember, is what we call the vertex form. And the form given right above over here, that's the standard form. And each of these forms is good for finding out a specific part of the parabola or the quadratic function. When it comes to the vertex form, it is good for finding the vertex, which is namely the values of p and q at the max or the minimum. And when we say p and q, for p, we're referring to the x coordinate, and for q, it's the y coordinate of the max or the min. So imagine I have a graph here, and I have, let's say, a quadratic that opens downwards like this. That maximum value here, that's the vertex. And the coordinates would be p and q, or x and y. So there's a couple of ways that you can convert this standard form into the vertex form. One of the ways is by doing something called completing the square. Now to complete the square, I'm going to bracket all the terms that have the x. So it'll be y equals bracket 2x squared minus 8x plus 2. And what I'm going to do is I'm going to take the term in brackets and try and turn it into a perfect square trinomial. And so in order to do that, remember that this is the a value here. We're going to factor this bracket out so that a is equal to 1. So if I go y equals, that'll be 2, and then x squared minus 4x plus 2. Now the next thing that we're going to do is, again, identifying that this is the a and this is the b, we're going to divide the term b by 2 and square it. Now the purpose of doing this is so that we can help create this perfect square trinomial. So b by 2, which is -4 divided by 2 squared, and this is going to be, well, -2 squared, which is going to be 4. And so what we're going to do now is insert this term right inside this bracket. So we're going to go y equals 2x squared minus 4x, and then we're going to go plus 4, and then plus 2. Now, in order to make sure that the ratio remains the same here, whatever we've added inside the bracket, we have to undo it somewhere in the equation. Otherwise, we're changing the ratio of the entire equation, which means that we're actually changing the equation. So I'm going to go plus 4, then minus 4. Now that 4 is also subject to the 2 because everything inside the bracket here is subject to the 2. So I would have to go 4 times 2. And so I go y equals 2 x squared minus 4x plus 4 plus 2 minus 8. I'm going to clean this up even further. I'm going to go 2x squared minus 4x plus 4 plus, and that'll, or sorry, it should be minus 6. So 2 minus 8 is minus 6. And then now what I should have inside this over here is a perfect square trinomial. So what I'm going to do is, for my third step, I'm going to factor that perfect square trinomial. Now, we can see that, again, I didn't show the full grouping over here, but if I did show it, you would get x minus 2 and x minus 2. And this is a perfect square because I got two of the exact same factors. I could rewrite that as follows. And so if I rewrite this fully, that's y is equal to 2 x minus 2 squared minus 6. And this is the fully converted vertex form of the equation. And with regards to our choices up above, then we know that the value of p is actually 2, since we set the brackets to 0. And q is negative 6, so the choice would be B. Now, an alternative and probably faster way that you could solve for the vertex is to use what we call the vertex formula. So it breaks down into two parts. The first part is to get the x value of the vertex. You can go negative b over 2a. And by b and a, we're talking about the standard form of the equation. So that's your a. Remember, that's your b, and that's your c. And so plugging this in, if we go minus 8 divided by 2 times 2, we see that, well, x is going to be 2, which is, well, what we found out before. And then once I have my x value, I can just take this and I can plug it into the original form, standard form of the equation. So wherever there's an x, I'm going to put the 2 here. And by plugging that into our calculator, we would also get a value of negative 6. And so either way works. Just do whichever one makes you feel more comfortable or that you are more confident in doing, and you're going to get the right answer. The idea is to understand that you're solving for the vertex, and how you do that is up for grabs.